Okay, now that that is out of the way, let me say first good morning, and let's start our discussion of chapter 3, which is basically, again, something you should have covered in introductory or high school chemistry, and that is stoichiometry. So stoichiometry, just to give a broad definition of what we're talking about here, stoichiometry is that area of chemistry which deals with quantitative relationships in a chemical reaction, the quantitative relationships between different substances in a chemical reaction. However, before we actually get to that part of it, we have to reintroduce ourselves to certain terms and certain types of problems that are related, all right? So the first term here, and I'm going to go through these quickly, of course, because as I said before, you should be familiar with these. So the first definition here is that of molecular mass. And basically that's the sum of the masses of all the atoms represented in a molecular formula. So just to give you a simple example, water has a formula of H2O. So therefore, if you want to find the molecular mass of water, you simply add up the atomic masses of all the elements according to the formula. So it's 2 times the atomic mass of hydrogen because you have 2 hydrogen atoms represented here, plus the atomic mass of oxygen. And in this particular case, the answer would be 18.0152 AMU. All right, so that's a relatively simple example. And you can apply this to literally any molecular formula, right? You just simply add up all the atomic masses according to the formula. Here's another one, sulfur dioxide, same idea. 1 sulfur, 2 oxygens per molecule. So therefore, that's why we multiply the atomic mass of oxygen by 2, and we add that to the atomic mass of sulfur. In this case, the answer is 64.065 AMU. And even something a bit more complex like glucose, for which the formula is C6H12O6. Again, it's the same idea. We multiply each of these atomic masses by their respective subscripts. So that's what you see here. And in this case, the answer is 180.1154 AMU. So that's basically how you calculate the molecular mass of any molecular compound, if you know, of course, what the molecular formula is. All right, and then we have something very similar called the formula mass. And this is basically the same thing as the molecular mass. The only difference is that the term formula mass is applied to ionic compounds, all right?
We can't see your screen.
Oh, I'm sorry. I keep forgetting. Okay, can you see now?
Yes.
Okay, so as I was saying, maybe I should go back to what I was talking about before. So I was talking about the molecular mass, and this is the water example I alluded to. Very simple example. Add up the atomic masses of hydrogen and oxygen according to the formula, and that's the answer for water. In the case of sulfur dioxide, this is it. Let me minimize this here. In the case of sulfur dioxide, this is it right here. And in the case of glucose, which is more complex, this is the molecular mass. But again, in both cases, it's the same principle applied where you multiply the atomic mass of each element by their respective subscripts in the formula, all right? So that's basically molecular mass. Now for formula mass, as I was saying, we use it in reference to ionic compounds, all right? And that's why we cannot use molecular mass when it comes to ionic compounds, because of course, in the case of ionic compounds, we have no molecules. So what we use to represent the formula for ionic compounds is basically the empirical formula for the particular ionic compound. So in the case of sodium chloride, for which the empirical formula is NaCl, basically we just simply add the atomic mass of 1 sodium atom to 1 chlorine atom, and that's what you get, all right? And that would represent, in this case, in the case of sodium chloride, the formula mass of sodium chloride, all right? So it's the same idea, same principle, but the only difference is that in the case of ionic compounds, we use the formula unit for sodium chloride, which is basically the empirical formula, all right? Okay, so that's formula mass. Another thing that you should know about from before is this number, Avogadro's number. right? Which is basically the number of elementary entities in 1 mole of anything. So Avogadro's number literally can apply to anything, any material object. You can have 1 mole of that, right? Now, Avogadro's number is equal to this large number here. For our purposes, we're just going to round off to 3 significant figures. So 6.02 times 10 to the 23 is what we're going to use to represent the number of entities present in 1 mole, and that would be Avogadro's number, all right? And the actual definition of a mole is given right here. A mole is an amount of substance that contains as many elementary entities as there are atoms in exactly 12 grams of the carbon-12 isotope. And it was discovered that 12 grams of the carbon-12 isotope contains 6.02 times 10 to the 23 atoms of carbon, all right? So that's the definition of the mole, and therefore that's how we end up with this number. And we can apply, as I said before, this idea of Avogadro's number to literally anything. So 1 mole of the stars of the universe would be that number, 1 mole of pennies, 1 mole of tennis balls, 1 mole of glucose molecules, helium atoms, potassium ions, they all have the same number of particles or entities, all right? Now, of course, when it comes to chemistry, it is more applicable to very small microscopic entities such as atoms, molecules, ions, protons, neutrons, electrons, etc. Right? So we tend to use the Avogadro's number in that context, all right? Okay, so when it comes to applying what we just learned with respect to Avogadro's number, you'll see that there's a relationship between the mole and the number of molecules or atoms participating in a reaction. So we're going to use a simple example, the example of carbon reacting with oxygen to form carbon dioxide. So this is basically the equation here, right? And as you can see, there's a 1:1:1 ratio between the carbon atom, the oxygen molecules, and the carbon dioxide molecule, right? So that's a straight up 1:1:1 relationship, all right, just to make things simple. So therefore, if 1 atom of carbon reacts with 1 molecule of oxygen, then we can say that 2 atoms of carbon will react with 2 molecules of oxygen. And we can, of course, go on and on to say 3, 4, 5, 6, 7, literally to infinity. But for our purposes, we'll stop at Avogadro's number. So therefore, given the 1:1:1 ratio that exists in this reaction, then we can say that Avogadro's number of carbon atoms will react with Avogadro's number of oxygen molecules to form Avogadro's number of carbon dioxide molecules, right? And we all know that this is 1 mole, this is 1 mole, this is 1 mole, right? So in a balanced equation, not only does the number of atoms are reflected in the balanced equation, but the mole relationships between the different substances involved is expressed in the equation as well, right? And as you can see here, 1 mole of carbon is 12.011 grams, 1 mole of oxygen is 31.9988 grams of oxygen, and 1 mole of carbon dioxide is 44.010 grams of oxygen, all right? So basically that shows you the relationship between the number of atoms involved in a reaction, the number of moles that are involved in the reaction, and also the masses of the atoms or the substances involved in the reaction. Another thing I want to talk about here, or point out here, sorry, is that, and this is kind of like a side note, this reaction here also demonstrates the conservation of mass law. If you remember, we said that the conservation of mass law says that in a chemical reaction, the amount of product formed mass-wise is the same as the mass of the product of the reactants involved. Well, you see that demonstrated here. If you add the 12.011 grams to the 31.9988 grams, you're going to get the 44.010 grams of carbon dioxide on this side. All right, so that's just a side note demonstrating the conservation of mass law. All right, so this brings us now to the concept of molar mass, right? So the definition of the molar mass of a substance is the mass of 1 mole of that substance, right? So whatever the mass that is observed for a mole of a particular substance, and it could be an element, it could be a compound, then that would be the molar mass. And it turns out that the molar mass is numerically equal to the atomic mass, or the molecular mass, or the formula mass, depending on whether or not you're talking about atoms, molecules, or ionic compounds, all right? So the difference between the molar mass and the atomic mass, molecular mass, or formula mass is basically the units, but the actual numerical value will be the same. So for example, in the case of sodium, if you go to the periodic table and you look up the atomic mass of sodium, you're going to see it's going to be equal to 22.99 grams, all right? What that means also is that the molar mass of sodium is going to be 22.99 grams per mole. And please note the units for molar mass, it is grams per mole, all right? So the unit of atomic mass or molecular mass or formula mass is AMU, but the units for molar mass is grams per mole, even though numerically they are the same. So we saw that in the case of sodium, and the same is true in the case of carbon dioxide. The molar mass of carbon dioxide is 44.01 grams per mole, right? Same unit, all right? So that's basically the relationship between the molar mass and the atomic mass, molecular mass, or formula mass. They're numerically the same, but the units are different. The units of molar mass is grams per mole, and the units of atomic mass, molecular mass, or formula mass is AMU, atomic mass units. Okay, so based on what we have learned, we can use the molar mass to do certain calculations, especially when it comes to converting from moles to grams and grams to moles. So in order for us to do that, it is convenient for us to express the molar mass in a fractional form. Since molar mass can be expressed in grams per mole, there are two ways of expressing molar mass in terms of a fraction. You can express it this way, where you have the grams above and 1 mole below, or this way, if you want to express it in terms of moles per grams, right? 1 mole above and grams below. And which of these you'd use is dependent on the type of calculation that you're trying to achieve. You would use this one if you're trying to convert from moles to grams. You would use this one if you're trying to convert from grams to moles, all right? So here's an example, all right? So the question says here, let me go back to my pointer. The question says here, calculate the mass in grams of 0.250 moles of ammonia, all right? So the first thing I would do in tackling this problem is that I would figure out what the molar mass is. So what I would do is go to the periodic table, look up the molar masses of nitrogen and the 3 hydrogens and add them up. So when you do that, as shown here, you see that the answer becomes 17.024 grams per mole, all right? So that's a molar mass. So the next step is that I would start off with the 0.250 moles of ammonia, and I will multiply by this conversion factor where I have the grams of ammonia above and 1 mole of ammonia below, right? So basically, that's the setup. I would do the cancellation, and I would end up with the mass being equal to 4.26 grams of ammonia, of course, when you do your calculation. And you'll notice that in this setup, the moles of ammonia will cancel out because the question is asking for you to calculate the mass in grams, which would be the remaining unit after you have done your cancellation and calculations. All right. Okay. Any questions so far? Any questions? Okay, no questions? All right, so let's proceed. So another concept I want to discuss here, again, this is something you should have learned earlier, percent composition, all right? So to demonstrate the whole concept of percent composition, we're going to use a non-chemistry example here. So here we have a collection of boxes or blocks. We have 4 orange blocks, and I don't know why they said green here. Looks like blue to me, almost purple. And if you want to find the percent composition by color, very simple. Basically, you divide the number of the colored blocks, the particular colored blocks, by the total number of blocks. So 4 orange blocks divided by 6, multiplied by 100, give you 67%. And of course, the 2 blue blocks divided by 6 will give you 33%. And of course, as you would expect, since there are only these 2 types of blocks present, then when you add the percentages, the 67 plus the 33, you will get 100%, right? So that's basically how this works. And you're going to see the same principle at play when it comes to percent composition of a substance, all right? So when we're talking about percent composition, right, in the vast majority of cases in regards to compounds, we're talking about percent by mass, all right? So that's why we have here the mass percent composition as a title right here, all right? So by definition, the mass percent composition is the ratio of the total mass of a given element in a compound to the mass of the compound. All right. So that's the definition of mass percent composition. So if you look at the example of this compound, now this compound is called butane. The formula is C4H10. All right. So in 1 mole of butane, based on this formula, excuse me, as stated here, there are 4 moles of carbon and 2 moles of hydrogen, right? I'm sorry, 10 moles of hydrogen, right? So that's in 1 mole of butane. So to find the total mass of carbon in 1 mole of butane, we multiply the 4, which is a subscript, by the molar mass of carbon, which is 12.011, and that will give you the total mass of carbon in 1 mole of butane, all right? So once we get that, we can also find the total mass of hydrogen in 1 mole of butane. According to the formula, hydrogen has a subscript of 10. So we multiply 10 by the molar mass of hydrogen and we get 10.079 grams of hydrogen present in 1 mole of butane. And then we add those two together to get the total mass of the total mass per mole, which would be the molar mass, right? Which is equal to 58.123 grams. So once we get that, to get the percentage of carbon present in 1 mole of butane, we take the total mass of carbon and divide it by the total mass of the entire compound, and we multiply by 100%, and this is the answer that we get here, 82.66%. And then it's not shown here, but basically you're going to do the same thing. In fact, let me do some scribblings here. To get the percentage of hydrogen, where am I going to squeeze this? Okay, let me see here. Hold on. Let me squeeze it up top here. Okay, so basically to get the percentage of hydrogen, that will be equal to the total mass of the hydrogen, which is 10.079%, 9 grams, I'm sorry, divided by the total mass, which is 58.12 grams times 100%. And where's my calculator? Okay, so let me work that out. So 10.079 divided by 58.123. And the answer I got is times 100. And the answer I got is 17 point, round off to how many sig fig? 5 sig figs. So that would be 17.0341. Hold on, let me see. 17.03. I'm sorry. 17.341 percent. All right. And of course, when you add the 17.341 to the 82.66, you'll get, if not 100%, a number very close to 100%. All right. Okay. Any questions about this example? Any questions? Any questions? Okay. So let's talk about molecular and empirical formulas. And we talked about these before, but we're going to get into more details about this, right? So if you recall, we said that the empirical formula is the simplest whole number ratio of the elements in the compound, right? It gives you actually the simplest whole number ratio of the elements in the compound. The molecular formula gives you the number of atoms of each element present per molecule. So going back to the glucose example we saw earlier, this is the molecular formula for glucose, right? This right here, C6H12O6. So what this tells you is that for every molecule of glucose, you have 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms, all right? So that's a molecular formula. That's information that you would get from the molecular formula. Now the empirical formula tells you the ratio of carbon to hydrogen to oxygen atoms, right? So therefore that ratio is 1 to 2 to 1, and therefore the empirical formula is CH2O. And of course, obviously, to get from the molecular formula to the chemical formula, we have to divide all the subscripts here, so the 6, the 12, and the 6 by 6, right? So when we divide those subscripts by 6, the resulting formula will be the empirical formula, all right? So it's very easy to get from the empirical formula to the empirical formula. Now, it's more difficult to get from the empirical formula to the molecular formula because you would have to get some information to know what you'll multiply the empirical formula by to get to the molecular formula. So we're going to see some examples of that in this chapter. All right. Okay. So what we're going to do is look at this example. And this is a typical empirical formula type problem where you're given some data, more specifically the mass percent data of the different elements present. And based on that data, you're required to determine the empirical formula. All right. Now, in this case, the question says a compound is comprised of 40.01% carbon, 6.72% hydrogen, and 53.2% oxygen. And the question is asking for you to calculate the empirical formula for the compound, right? Now, the very first step that you would make in tackling a problem of this type, excuse me, is to determine or to make an assumption. And the assumption you'll be making is the assumption of a certain amount of mass of the sample of the compound. Now, for the sake of pure convenience, we can assume 100 grams of the substance. And the reason why we can assume that is because once we assume that we have 100 grams of the substance working with, then each of these numbers that we have for the respective elements, the percentages, will automatically become the grams of each of those elements present in 100 grams of the substance, all right? You could actually assume any number, right? But 100 grams is, of course, most convenient for us to use because we don't need to do any and we don't need to add an extra step to the calculation. We can just simply assume that these numbers here represent the masses in grams of each element present in 100 grams, all right? So that's the first step. Now, once you determine that, what I'm going to do is, well, let me copy and paste this here. Copy this here and paste it in this, okay, in this PowerPoint document here. Okay, so that I can have it to look at while I'm doing the problem solving. All right, so now that we have this here, let me make it full screen. All right, so they gave you 40.01% of carbon, 6.72 grams, I'm sorry, percent of hydrogen, and 53.2% oxygen. So therefore, what I'm going to do here is construct a table. So at the top of the table, I have carbon, hydrogen, and oxygen, all right? So the first thing I will do is, whoops, I'm going to record the masses, I'm sorry, the masses of each of these elements, remembering that I'm assuming that these numbers would be the same as the masses because we're assuming 100 grams. So I'm going to put 40.01 grams of carbon. I'm going to put 6.72 grams of hydrogen, and I'm going to put 53.27 grams of oxygen, all right? So that's the first step. The next step is that I'm going to find the moles of each of these, right? So in the case of carbon, and how do we find the moles, by the way? Well, we take the mass of each of these and we divide by their respective molar mass. So in this case, it's going to be 1 mole over 12.01 grams. In the case of hydrogen, it's going to be 1 mole over 1.008 grams. And in the case of oxygen, it's going to be 53.27 grams divided by, well, multiplied by 1 mole over 16.00 grams, all right? So of course, in each of these cases, the gram units will cancel out and you'll be left with moles. So let me do the calculation for carbon. So it's going to be 40.01 divided by 12.01. And according to my calculations, rounded off to 4 sig figs, this would be equal to 3.331 mole. I'm going to do the same thing for hydrogen, 6.72 divided by 1.008. So according to my calculations, this will be rounded off to 3 sig figs, so this will be 6.66. So here I'm going to write 6.66 moles. And then in the case of oxygen, I'm going to divide 53.27 by 1/6. And according to my calculation, this works out, how many sig figs? 4 sig figs. So this would be 3.330. So 3.330 moles, all right? So what we have calculated up to this point would be the moles of each element present in 100 grams of this compound. The next step is that we examine each of these numbers, this one, and decide which one is of the lowest value. And we divide each of these by that value, all right? So the lowest one would be this one right here. So what we're gonna be doing in this line is dividing by that value, 3.330 moles, all right? So let me do it on my calculator. So 3.331 divided by 3.330. According to my calculation, this gives you 1.000. And let me do 6.66 divided by 3.330. And according to my calculation, that gives you exactly 2, but of course you have to make sure you round off to 3 sig figs. And then finally, well, that divided by itself will give you 1. So I'm just going to put 1 right here, right? 0.000. So what we're going to do next is that these numbers here, we round off to the nearest whole number. So this is going to be 1, this is going to be 2, and this is going to be 1, right? So therefore, the empirical formula for this compound here would be C1, which you don't have to put, but let me put it here anyway, H2O1, or you can just simply put CH2O, all right? So what you have noticed here is that these numbers here that I've calculated here becomes the subscripts in the empirical formula for the respective elements. And that's basically how you tackle a problem of this type, all right? Okay, any questions about this particular example? Any questions? Any questions?
No, sir.
Okay, all right, so let me get out of this. You know what, I think I'm gonna keep this. Let me go back to the PowerPoint. And here we have 2 examples, right? So we're gonna go through both examples. Let me skip this, let me copy this. And then create a next slide. Let me get this out of the way. Okay. Okay, so this is another, let me make this smaller. I might need some more space. Okay, you all should be able to see this. So, all right. So based on what we have discussed so far, based on the example that we just looked at, we're gonna do this problem. Give me 1 minute, let me turn on the fan here, hold on. Okay, sorry about that. All right, so based on what we have done before, what would be the very first step that you would take to solve this problem? What's the first step? Anybody?
Make a chart with the percentages.
Okay, so carbon, whoops, what's going on here? Carbon, hydrogen, and oxygen, right? And remember, we said that we assume the percentages would be the same as the masses because we're assuming 100 grams, right? So this row here would be the mass row, right? So we're going to put 76.57 grams, 6.43 grams, and 17.00 grams. Let me move the line, this line here, a bit further to the right, so as to create some space for the carbon column. Okay. All right, so the next step would be what?
Find your moles.
Okay, so to find the moles, we multiply 76.57 grams by what?
1 mole over 12 grams.
12.01 grams. All right. And then for the hydrogen, we multiply 6.43 grams by what? 1 mole over
1 gram.
0.008 grams. Exactly. All right. And then in the case of oxygen, we multiply that by 1 mole over
16.
16.00 grams. Okay. So let me work this out. And folks, let me just say this. While I'm working, like doing calculations like these, you should do it as well, because I could be doing the wrong thing and we want to get the right answer. So while I'm doing these calculations, you do it as well to ensure the accuracy. So in the case of carbon, it's 76.57 divided by 12.01. And according to my calculations, rounded off to 4 sig figs, that would be equal to 6.376. 6.376 mole, all right? And then in the case of hydrogen, 6.43 divided by 1.008. According to my calculations, when rounded off to 3 sig figs, that becomes 6.38 moles. And then in the case of oxygen, 17.00 divided by 16.00. And according to my calculations, this rounds off to 4 sig figs, so this should be 1.063. 1.063 moles, all right? Okay, so the next step would be what?
Divide by your lowest.
Okay, so the lowest is this one right here, right? So that means that you're going to divide right through by 1.063 moles. So obviously you're going to get 1 here since you're dividing it by itself. So let's see what happens when you divide 6.376 by 1.063. And according to my calculations, when rounded off to 4 sig figs, that gives you 5.998. 6.38 divided by 1.063. According to my calculation, this part gives you, rounded off to 3 sig figs, 6.00, all right? Okay, so basically, upon inspection, you'd notice that this is very close to 6, right? So this would be approximately 6, this would be approximately 6, and this would be 1. So therefore, in this case, the empirical formula is equal to C6H60. And that's how you do that one. All right? Any questions? Any questions?
No, sir.
Okay, all right, so this, no, not this card, let me keep this. Let me go back to this one here. So this is another problem, all right? Again, you're asked to determine the empirical formula, right? So let me copy this, go back to this, create a new slide, put that question here. Oh shoot, hold on, I guess I didn't copy it. Copy. Oh, it took its time. Okay, I did copy it. Oh, okay. Let me do this. And bring this down. Try to make the font smaller. And then, okay. So similar problem, same elements actually, but different percentages. And again, the same task is what you're given to determine the empirical formula. Okay, so like before, we're going to construct a table, carbon, hydrogen, and oxygen. Again, we're going to assume that the percentages are the same as the masses. So in the case of So mass here for this row. In the case of carbon, it's going to be 45.27 grams. In the case of hydrogen, it's going to be 9.50 grams. And in the case of oxygen, it's going to be 45.23 grams, all right? So the next step would be to find the moles. And in this case here, we're going to divide or multiply 45.27 grams by 1 mole over 12.01 grams. In the case of hydrogen, it's 9.50 grams multiplied by 1 mole over 1.008 grams. And in the case of oxygen, it's 45.23 grams multiplied by 1 mole over 16.0 grams. I'm sorry, 0.00 grams, all right? So in the case of carbon, it's 45.27 divided by 12.01, and that would be equal to, round off to 4 sig figs, so that would be 3.769 moles. In the case of hydrogen, we multiply divide 9.50 by 1.008. And according to my calculations, round off to 3 sig figs, you're going to get 9.42 moles. And then finally, in the case of oxygen, 45.23 divided by 16, and you're going to get 2.827, round off to 4 sig figs moles. All right. Okay. So the next step is what? What's the next step?
Divide by the lowest number.
Which is
The
2.827, right?
Yes.
So we're going to divide by 2.827 moles. So in the case of carbon, that would be 3.769 divided by 2.827. So the answer I got here is 1.33, how many sig figs? 4 sig figs. So that would be 1.333 moles. And in the case of hydrogen, it's 9.42 divided by 2.827. And according to my calculation, this gives you 3.332. Oh, by the way, the moles will not be there because the moles will cancel out as a result of that. So there should be no units when we do this part. And then this would give you 1, all right? Okay, now, what do you think we should do from this point? Anybody?
Round the 1 up to a 2 and round the 3 up to a 4.
No, can't do that. And the reason why we can't, let me just explain. The reason why we can't do that is because these numbers that you were just referencing, this number and this number, they are too far away from the nearest integer for you to just round up or round down, right? So typically, if there is like, what's the rule? Oh gosh. If it's less than 0.1 from the nearest integer, I'm sorry. Well, yes, if it's less than 0.1 from the nearest integer, then you can round off. But if it is not, then you can't do that. So what you need to do is that you need to, let me create another row here. You need to multiply all these numbers by a certain integer to convert these numbers into integers down here, right? Now, you can get a hint as to what that number is by looking at the number of digits or the type of digits after the decimal point. You'll notice, for example, that you have a recurring 3 after the decimal point here, right? Now, if you have a recurring 3 after the decimal point, that is basically approximately the same thing as 1/3, all right? So to convert any number that has recurring 3 after the decimal point into an integer, then you simply multiply that by 3, because 3 times 1/3 will give you an integer, which is 1, all right? And you see that you have a kind of recurring 3 after the decimal point, even though you have a 2 here. So basically what you'll do in this case is that you multiply right through by 3, right? So when you multiply right through by 3, the 1.333 times 3 gives you 3.999. And the 3.332 times 3 gives you 9.996. And of course, when you multiply 1 by 3, you're going to get 3, right? So now you have a number which is very close to an integer here. The 3.999 is approximately 4, right? And the 9.996 is approximately 10, all right? So therefore, the empirical formula for this compound will be equal to C4H10O3. And that's how you do that type of problem. So unfortunately, there are some situations where when you get to, oops, what's going on here? Oh, I know. Okay. When you get to this stage here, you'll get some numbers here which will not be close to an integer. And therefore, you have to figure out what do you need to multiply these numbers by to get an integer, to convert these numbers into an integer, all right? And let me just say this, that as I said before, you can get some clue as to which numbers, what type of number you need to multiply to convert your numbers into integer by looking at the numbers after the decimal point. Let me go to this tablet here to explain this further. So okay, so if you have a recurring 3 after the decimal point, right? That is the same thing as 1 over 3, all right? So therefore, if you want to convert this into an integer, you multiply by 3, right? And that will give you, in this case, 1. Now, there are some other situations. For example, if you have a recurring 6 after the decimal point, right? That would be the same thing as 2 over 3. So in this case, you'll multiply by 3 again to convert it into an integer, which in this case would give you 2. If you have 0.5, right? In other words, 5 after the decimal point, that is the same thing as a half, which means that you'd have to multiply by 2 to convert that to an integer, which would be 1. If you have 2.5 after the decimal point, such as 0.25, 0.25 is the same thing as 1 over 4. So that means that you'll multiply by 4 to convert this to an integer, which in this case will be 1. If you have 0.75, or if you have 7.5 after the decimal point, 0.75 is the same thing as 3 over 4. So if you multiply by 4, that will give you an integer, which in this case will be 3. There's another one. If you have a recurring 1 after the decimal point, right? That would be the same thing as 1 over 9. So you multiply both sides by 9, and that will give you an integer, which would be, in this case, 1, all right? So those are the examples I can think of from the top of my head. I can't think of any, but there are a lot more, right? If you don't see any of these patterns, right, then basically what you'd have to do is trial and error, right? Try different numbers, multiply by different numbers so as to get the correct integer, and therefore you can get the correct empirical formula, all right? Okay, any questions about this? Any questions? Any questions? All right, okay, so what's next? Okay, elemental analysis. Yeah, let's talk about this. Okay, now this is something I'm very sure that you have not met before in your high school or introductory chemistry. So I'm going to take my time explaining what is involved in this process. So elemental analysis, as the name suggests, basically involves determining what elements are present in a particular compound and how much of each element is present. In other words, basically what you'll be determining is the empirical formula, all right? So this is usually applied to organic compounds, but also can be applied to other type of compounds as well. So we're going to stick to a discussion of elemental analysis with regards to organic compounds. So when we're talking about organic compounds, we're talking about compounds containing carbon, hydrogen, and oxygen, right? In fact, you can have organic compounds containing carbon and hydrogen only, and those are called hydrocarbons. And then you can have compounds containing carbon, hydrogen, and oxygen. And you can also have other elements present as well, all right? Halogens, nitrogens are the usual other elements that can exist in an organic compound, all right? So the way this works is that the compound is burned in oxygen. And this is something that you should know from your previous experience. When you burn an organic compound, any compound that contains carbon, hydrogen, and oxygen, you're going to get products. And the products will be carbon dioxide and oxygen. And that's assuming that the combustion is complete, all right? You have burned the compound completely, and therefore you're going to end up with carbon dioxide and water, all right? Now, in this process, some method is used to collect these two products, the carbon dioxide and water, and they're weighed, right? And then based on the masses of the carbon dioxide and water that you have determined, then you can work backwards to determine the mass of carbon and hydrogen present in the original compound, all right? And also you can determine the presence or the amount of the other elements as well, all right? So that's basically what is involved in elemental analysis. Now, the next slide I'm going to show you is actually a schematic representation of the actual experiment, all right? So what we have here are three compartments connected to each other, right? One compartment is basically the furnace. That contains the organic substance, okay? So basically, heat will be applied to this, oxygen will be forced into this compartment, and the sample will be burned. As I said before, upon complete combustion, the two products formed would be carbon dioxide and water, all right? So those products would be led to the other compartment, and this compartment contains a substance which will absorb the water. In this case, the substance is magnesium perchlorate. There's another alternative substance which I can't recall now, but we're going to go with the magnesium perchlorate, right? So we have to ensure in this part here that we have enough of the magnesium perchlorate to absorb all the carbon dioxide that was produced as a result of burning the sample, all right? So if that's the case, the only other substance that should emerge from this compartment would be the carbon dioxide. So that carbon dioxide is led into this compartment. And the compartment here will contain a substance which will absorb the carbon dioxide, which would be sodium hydroxide. You can also use potassium hydroxide as well for this part of the experiment. Again, you have to ensure that the amount of sodium hydroxide here is enough to absorb all the carbon dioxide that is emerging from this compartment here, all right? So basically the way we actually do this experiment is that you start off with your sample here. You make sure that you weigh the amount of magnesium perchlorate here. You weigh the sodium hydroxide. Of course, you weigh the amount of the sample here. And then after everything is burnt, and this absorbs the water and this absorbs the carbon dioxide, you separate the compartments. You weigh the magnesium perchlorate, and you should observe a mass increase because now it has absorbed water. You weigh the sodium hydroxide. Again, there should be a mass increase because it absorbed the carbon dioxide. And then based on those masses, you can do your calculation of the empirical mass. And in fact, we're going to do an example of this type of calculation, I think in the next slide. But this is just showing you basically how an elemental analysis for an organic compound is conducted. Okay, so let me just skip all this here because I already described what's happening here. So we're going to go directly into this example. So let me exit this. And let me copy this. Let me go here. Let me go here. Let me escape this. Let me keep this. Let me create another slide. And then let me copy and paste. Oh, no. Why did this happen? Okay, let me do this. Let me. Okay, I don't know why it went to a white colored font. Okay, so this is the question. Let me again make this smaller. Okay, so this is the question. Oh, it looked like I make sure I'm including every piece of information. Okay. Okay. Um, ah, all right, enough of that. Okay, so in this question, which is a typical question of this type, combustion analysis question, it talks about menthol, and it talks about, let me go to full screen. It talks about menthol, and it says that they start off with, it says that menthol contains carbon, hydrogen, and oxygen, all right? And then it's starting off with a 0.1005 gram sample of menthol. And it says that when it is combusted, it produces 0.2829 grams of carbon and 0.1159 grams of water. So the question is asking, what is the empirical formula for methanol, all right? For menthol, I'm sorry. So let me start off with the 0.2829 grams of carbon dioxide. Okay, now, as we said before, if a compound is burnt in oxygen, so let's say this is a general formula for the compound, CHO, right? We don't know how many carbon, hydrogen, or oxygen atoms are present, but when this reacts with oxygen, it forms CO2 and H2O, all right? So if we know the mass of carbon dioxide that is produced, then we can work backwards to find out the mass of carbon that was there in the original compound. And the same thing with the water. If we know the mass of water, if we know the mass of water that is produced, we can work backwards to find out the mass of hydrogen, right? And if we know the masses of carbon and hydrogen as a result, then we can add those two and subtract it from the original mass of the compound to get the mass of the oxygen. So what I've just described is an overall strategy for solving this problem. So what we're going to do is start off with the 0.2829 grams of carbon dioxide. And the first thing we're going to do is convert it to moles. So we're going to have 1 mole of carbon dioxide here. And the molar mass of carbon dioxide, if you add up the carbon and the oxygens, you're going to end up with 44.01 grams of CO2. All right, that's the first step. All right. Okay. So the next step, sorry for the confusion here, is to find the moles of carbon present in the given moles of carbon dioxide that you'd have formed or determined at the first step. And based on the formula here of carbon dioxide, you can see that for every 1 mole of carbon dioxide, you have 1 mole of carbon, all right? So far up to this point, we have determined the moles of carbon, but remember we need to determine the mass of carbon. So therefore the next step is where we convert the moles to mass, and that would be, the way we do this is that we have 1 mole of carbon down here, and the molar mass of carbon above, which is 12.01 grams, all right? And that's basically how you get the mass of carbon. So let me do that work here. And again, please work with me, do the calculation so that you ensure that I'm doing the right thing. So 0.2829 divided by 44.01, and then multiply by 1, multiply by 12.01. Now that, according to my calculation, gives 0, how many sig figs? 4 sig figs. So 0.07720 grams. All right, so that would be the mass of carbon present in that compound. Then we do a similar calculation for the water. So we're going to start off with the given mass of water, which is 0.1159 grams of H2O. We multiply by 1 mole of H2O. divided by the molar mass of water, which is 18.02 grams. And let me say something about the next step. The next step is going to be similar to what we did at this point here in the case of the carbon dioxide. But students always mess up on this step right here. Oh, shoot, what's going on here? Okay, so the next step is where we look at the mole ratio between the water and the hydrogen present in the water. Now, please note that there's a 2 here as a subscript, right? So what that tells you is that for every 1 mole of H2O, there are 2 moles of hydrogen, all right? So you should have a 2 here. Very often students, for some reason, neglect to include a 2 there and put a 1 instead, all right? So please make a note of that. At this point, it should be 2 moles of hydrogen divided by 1 mole of water. And then the next step is where you convert the moles of hydrogen to mass. So you're gonna put 1 mole of hydrogen here and 1.008 grams of hydrogen above. So of course, you're gonna have some unit cancellations here. Moles of hydrogen will cancel out as well as the moles of water. So the only unit here would be the grams of hydrogen. And according to my calculations, which I'm about to do, 0.1159 divided by 18.02 times 2 times 1.008. Okay, so according to my calculations, this would be equal to 465, so that would be 0.01297. All right, so this would be the mass of hydrogen, this would be the mass of carbon. But remember, there are 3 elements present. You have carbon, hydrogen, and oxygen. So the question now becomes, how do we determine the mass of oxygen? And it's quite simple. Remembering that this is the total mass of the compound, right? The 0.1005 grams is the total mass of the compound, and we have the mass of 2 of the elements present, right? Namely, the carbon here and the hydrogen here. So to get the mass of the oxygen, what we do is that we take the total mass of the compound and we subtract from that the mass of the carbon, which is 0.07720 grams, added to the mass of the hydrogen, which is 0.01297 grams, all right? So that's how we get the mass of the oxygen. So let me work this out. So what I'm going to do is work out what's in the parentheses first. So 0.07720 plus 0.01297. Okay, so and then I'm going to subtract that from the 0.105 or 0.1005. So 0.1005, subtract that. Okay, so according to my calculations, the mass of water would be equal to 0.0, okay, so how many decimal places? It would be 4 decimal places, so 0.0103 grams, all right? So now we have the masses of carbon, hydrogen, and oxygen. So we need to now construct our table. So what I'm going to do for that purpose, I'm going to open this up. I'm going to, and what I'm going to do is start off with carbon, hydrogen, and oxygen. Now the mass of the oxygen is 0.0103. And the mass of the hydrogen is, what's the mass of the hydrogen? 0.01, no, what am I saying? Yeah, 0.01297. And the mass of the carbon is 0.07720 grams, all right? So, oh shoot. All right, I'm sorry about that. I thought I was writing at the top. Let me just rewrite this up here. Carbon, hydrogen, oxygen. Mass. Okay, so here we're going to have 0.07720 grams. Here we're going to have 0.01297 grams. And here we're going to have 0.0103 grams. All right, so these are the masses of all the elements. And basically, we're going to do the same thing as we did before. First step would be to determine the moles. Let me erase this down here to avoid confusion. Okay, so to get the moles, we're going to take 0.07720 grams multiplied by 1 mole over 12.01 grams, and then 0.01297 grams multiplied by 1 mole over 1.008 grams. And then finally, in the case of oxygen, 0.0103 grams multiplied by 1 mole over 16.00 grams. And then we find, oh, I shouldn't have done that. Let me erase this here. So we're going to do the calculations here at this point. So in the case of carbon, I'm going to divide 0.07720 by 12.01. And according to my calculations, this works out to be equal to, rounded off to 4 sig figs. This is going to be equal to 6.428 times 10 to the minus 3 moles. And then in the case of hydrogen, it's going to be 0.01297 divided by 1.008. And according to my calculations, this works out to be equal to 0.01287. Okay, and then in the case of oxygen, it's going to be 0.0103 divided by 1.6. And according to my calculations, this works out to be equal to 6.43 times 10 to the minus 4 moles. All right, and then we divide by the lowest. So which one is the lowest? Looks like oxygen, yeah, this one right here, right. So we're going to divide right through by 6.43 times 10 to the minus 4 moles. So when we do that for 6.426 times 10 to the minus 3 moles by 6.43 10 to the minus 4 moles. So let me do that here. 6.426 divide, I'm sorry, 6.426 times 10 to the minus 3 divided by 6.43 times 10 to the minus 4. Okay, so according to my calculations, when rounded off to 3 sig figs, this part works out to be equal to 9.99. All right, so that's how that works out. And then here, I'm going to take 0.01287 moles divided by 6.43 times 10 to the minus 4 moles. And according to my calculations, 0.01287 divided by 6.43 times 10 to the minus 4. Okay, so according to my calculation, this works out to be equal to, let me see, 3 sig figs, 20.0. And then this, of course, would give 1, right? So, of course, this here is very close to 10. So we can approximate that to 10. So therefore, the empirical formula here is equal to C10 H20O. All right. So as you can see, when it comes to combustion analysis problems of this type, there are two major steps, I would say. The first step is what we had here, where you have to determine the mass of each element present. And this is how we did it. And then the next is here, where we do the typical combustion analysis, or I should say empirical formula determination, like the examples that we have looked at earlier. All right. Okay. So as you can see, it's kind of long and involved, and you have to be careful. As you can imagine, if you make a mistake anywhere in this type of problem, it can screw up your final answer, right? And let me emphasize again, and I can't emphasize this enough. Let me go back to this here. Let me emphasize here that when you are determining the mass of hydrogen, when you get to this stage, make sure that there's a 2-to-1 ratio here between the mole of hydrogen and the moles of water, right? I can't tell you how many times students make that error where they forgot to put the 2 here and they put a 1 instead, all right? 2 moles of hydrogen for every 1 mole of water, and then that would lead to the mass of hydrogen. Because if you made that mistake here, this will be wrong, this will be wrong, and everything afterwards would be incorrect, all right? Okay, any questions about this particular example? Any questions? Any questions? Any questions? Okay. What's next? I thought there was another example. Hold on, let me check something here. Okay, I thought there was another example. All right, I'm going to stop here for today because the example I'm thinking of is one where you can convert from the empirical formula to the molecular formula. And I think it's very important that you understand that example. So I'm going to find that example, and that's what we're going to start off with for the next class, all right? Okay, any general question? Well, before any general questions, let me just say that you may have noticed your first assignment or quiz. So that, if I'm not mistaken, is due on Friday, all right? So make sure that you complete it and turn it in on Friday. If you encounter any difficulty with any of the problems in that exercise, please let me know. You can email me, or you can, I prefer actually if you Skype me, but if you want to email me, that's fine. I prefer Skype because sometimes it's very difficult to explain, you know, the final details of problem solving by email, all right? So I would prefer if you contact me via Skype, all right? You can contact me during the office hours that you see in the syllabus, all right? Okay, any other questions, general issues, whatever, any questions?
For the quizzes, do the answers have to be like the right amount of sig figs for
Yes,
each question?
exactly.
Or
Right.
even the ones where you don't ask for the sig figs?
Right, exactly. Any problems involving calculations, right?
Okay.
Multiplication, division, addition, subtraction. Yes, you have to make sure that you round off to the correct number of significant figures. All right? Okay, any other questions? Any other questions? Okay, so if there are no other questions, that's basically it for today. All right, so I'm going to see you guys on Thursday. All right, so take care and have a good day.